Hi everyone. So today we are going to start with another part of this phase change processes heat transfer. So in the last class we have discussed about boiling heat transfer. We have discussed the difference between boiling, condensation and evaporation. So we have had a detailed analysis of what are boiling is, what evaporation is, what condensation is, then the types of boiling. We have discussed in details about the pool boiling and the regimes of flow boiling, have understood the fundamentals of evaporation and how does the boiling takes place, and what are the terminologies that come into picture while we analyze the boiling, what are the regimes, pool boiling, nucleation, critical heat flux terminologies, what does that mean. So today we are going to start with the another portion of a phase change process, that is condensation heat transfer. So here we will end the phase change process. Like we have three different processes: boiling, evaporation and condensation. So evaporation basics and fundamental, that has been discussed in details. Boiling we have studied in detail, and today we will be concluding with this condensation heat transfer, and in the next class we will be shifting towards the heat exchanger, that is going to the end of our heat transfer course. So in today's class we will study and analyze about this condensation heat transfer, and once it is done we will have previous year GATE questions regarding this boiling and condensation. So I will try to solve 2-3 problems of this boiling and condensations that has been asked in previous year GATE examination. So then once all those theory lectures has completed, we will go and solve the problems that is on conduction, convection, radiation and heat exchangers. So let's start with today's class of condensation heat transfer. So prior going to start with what condensation is, what does it means, let's have a clear picture about onto the examples of condensation. Okay, so if we will see or remember that what condensation is, then we can remind that we have studied and analyzed and discussed in the last class that if we will make a fluid or a liquid that is in its vapor phase, and we will change its phase from vapor to liquid stage, the process is called as condensation. Let us take a day-to-day life example. आपने कोल्ड ड्रिंक्स की बोतल देखी होगी. When you take it out from the freezer and keep it on a table, immediately at the vicinity of the surface water droplets and films form. वो क्यों होता है? In the air that is adjacent to the surface of that cold drinks bottle, what happens to there? The air is a mixture of gases. उसमें water vapor भी होता है. So when that water vapor comes in contact with the surface whose temperature is very much low as compared to the ambient temperature, that is which is low as compared to the saturation temperature of the gas at the corresponding pressure, then it starts emitting its energy. Then the phase change takes place and it starts condensing. If we will go to analyze it in a very detailed way, let's have an example of that. Hope this screen is visible to you. Now let's see. Suppose this is my container, and this container, supposing it is at 2 degrees Celsius. Okay, then the vicinity air, the air is at ambient temperature, supposing if current's ambient temperature 50 degree Celsius. Then if it is at 2 degrees Celsius, this air that is in the ambient, it is a mixture of gases. As a chemical engineer, you know what are the main constituents of that: nitrogen, oxygen, carbon dioxide. Then it has some constituents of water vapor also. So this water vapor saturation temperature corresponding to the partial pressure of that which is present in the ambient, corresponding to that, when it comes in contact with a surface whose temperature is very much low corresponding to the saturation temperature of that liquid at the given pressure. फिर क्या होगा? This water vapor, it is at high energy state, that's why it is in the gaseous form. This gaseous form will try to release energy flow from high energy. The heat is transferred from high temperature to low temperature. So the water vapor is now at 50 degrees Celsius. Let's imagine all the gases are in thermal equilibrium with each other. If it is in the thermal equilibrium condition, then every component of gas will be at the same temperature, and suppose the water vapor is at 50 degrees Celsius, then okay, let's say that this air is at thermodynamic equilibrium. So अगर ये thermodynamic equilibrium में है, then the water vapor content in that will be at 50 degrees Celsius and the substrate is at 2 degrees Celsius. Then the water vapor will start releasing energy to its 2 degrees Celsius bottle. फिर क्या होगा? As it will dissipate its energy, it will come to its low energy state. Matlab, if we will remember the TS diagram, then if this is the dome, this is a constant pressure line. Now water vapor, suppose this is the point where the water vapor was. Then gradually when it starts releasing energy, it will move in this direction. So this is a two-phase direction. That means gradually the vapor will try to change its phase from high temperature to low temperature. It will change its phase from this gas to liquid, and it will move correspondingly downwards. Then while moving downward, it what will happen over here? It will change its temperature to the saturation temperature, in which it will be at the complete liquid state. Means this 50 degrees Celsius will form some droplets around it, and this droplet will be having the temperature. This droplet, this is basically the condensate form of the water vapor that is present in the ambient. So what will be the temperature of this droplet, and whether it will be in this drop manner or it will be like a film manner throughout the periphery of the surface. All these things in detail we are going to study and analyze in this chapter of condensation heat transfer. So in the condensation heat transfer, condensation occurs when the temperature of the vapor is reduced below its saturation temperature. As discussed, it can be in film form or in a droplet wise of form. So condensation are primarily distinguished into two types. One is film condensation, another is drop-wise condensation. So to moving towards the drop-wise condensation, what is a very good example of a drop-wise condensation? You have seen we have a beaker or a container having water in that. Let's cover it up with a plate. जैसे कि हम पानी उबाल रहे हैं या चावल बना रहे हैं, then at that time when you will just slide the cover and make it upside down, you will see continuous drop of water have formed over there. The condensation of the vapor that has been generated by heating, that has been condensate over the periphery in droplet manner. So that is a real life example of what drop-wise condensation is. Then film-wise condensation is like in the wall of a refrigerating device. You may say the refrigerant water cooler or something. Behind that we can feel a layer kind of a substrate or liquid or water has been formed because of this phase change, and that is called as the film-wise condensation. So in this film-wise and droplet, let us assume it in a physical way, that suppose let the saturation temperature of water at corresponding to ambient temperature, ambient pressure be 100 degrees Celsius. I have kept the surface as 80 degrees Celsius. Then condensation will definitely happen because temperature is low and it will change its phase. Then what will happen? If the condensate weights the surface thoroughly by forming a liquid film, it will be called as a liquid, or it is called liquid film condensation or film condensation. Here the whole surface is blanketed by the liquid film. As the whole surface is blanketed by the liquid film, the surface resistance towards the heat transfer will be severe. Okay, whereas in droplet, what happens? Some portions are occupied by the water drop, some portions are open to the ambient, some portions are condensate to that, some portions have open space. So this causes the change, means less resistance occurrence to the heat transfer process. So the convective heat transfer coefficient of a droplet condensation is higher as compared to the film condensation, and theoretically they tells that the HTC for the droplet condensation is nearly equal or in order of 10 as compared to the HTC of the film condensation. Hope this is clear to you. Then we will be moving on to the droplet wise the condensate vapor forms. Droplets on the surface, the droplet will slide down when it will reach a sufficient size, and here there is no film to resist the heat transfer, as the space is there, some area is exposed to the ambient to make the heat transfer process occur, we may say occur nicely or in a proper manner as compared to the film condensation. So the heat transfer coefficient is higher for droplet condensation as compared to the film wise condensation. So let's discuss on a whole about this film condensation. Okay, this is a perfect example of a film that is being formed on a surface. So here let's see that when the surface is there, condensation will happen, then it will form, supposing, hope you can see my palm. Okay, let's see this surface of the upside part of my palm. This is the surface and my condensation is happening, so it will form a film over this surface. Okay, so when this film forms on the top of the surface plate, it flows downward under the influence of gravity. It will definitely flow down under the influence of gravity. So when it flows down, the thickness of the film increases. Let the thickness of the film be delta, and delta increases when we move in downward direction under the influence of gravity. Suppose HFG is the amount of heat that is rejected during the condensation, because it's a phase change process where heat is transferred from higher energy state to lower energy state, and phase is changing from a higher energy state to lower energy state. So latent heat of energy will be releasing. So the latent heat of the latent heat during condensation, suppose it be HFG, then what we know that the surface temperature will definitely be below the saturation temperature for the condensation to happen, and the temperature of condensate is at T saturation at the interface and decreases gradually to the surface temperature at the wall. Here the interface is the immediate vicinity where the vapor is transforming to the liquid, and then at the wall the temperature will be equals to the wall because of the thermal equilibrium. So let's picturize this in this diagram. क्या होगा? Suppose this is a plate. Let me shade this. This is your plate. Okay, suppose the surface temperature of plate is Ts and this is the vapor. Under the significant action of gravity, the vapor will flow in upward downward direction. Then the condensate that forms over here, the film manner, starts forming in this manner, and the thickness over here is delta. M dot x is the mass flow rate in the x direction, if this is I consider to be my x direction. Then this layer is my liquid vapor interface, where my vapor and liquid are touch, or just from this point this vapor is being transferred to the liquid. Like here the vapor is being transferred and the interface where the liquid and vapor are meeting. So this temperature will be at T saturation, but gradually when this film comes here and at this point the liquid film temperature will be as T surface. That means suppose TV infinity is the temperature of the vapor, then gradually at the interface the temperature will be Tsat, then gradually the temperature will decrease to Ts. So this is the temperature distribution, that it will be higher in the vapor phase, then it will reduce gradually and will become Ts at some point. At the, what is that some point? That some point is the surface. So it will be at some temperature, then it will reduce, then it becomes you can say here that same boundary layer concept comes into picture, no jump condition, no temperature jump condition. Then here the temperature of the condensate at this point will become the surface temperature. Now if we'll move on to the velocity distribution, what here we are going to see is that the velocity with which the vapor is flowing, suppose let us take it is at uy, then at the somewhat below the interface where the gravity effect is more, the liquid film flowing at a very high velocity, then at the plate the velocity will be 0 because of no slip boundary condition. Same here it is applied, no temperature jump boundary condition, here it is applied, no slip boundary condition, then the velocity will increase. Then at the vapor the velocity will decrease because here the condensate is forming, because of its weight or the flow rate and the gravity, it will fall at a faster rate as compared to the velocity of the vapor, and the velocity of the vapor at somewhat will be less because the velocity, the vapor is at static condition. So this is how the velocity trend of a film condensation looks like, that it will be 0 at the plate, then it will gradually increase, then again it will decrease to some point 0 because the velocity of the vicinity vapor is not there, the vapor is stagnant, it is not flowing anywhere. So this is the overall nomenclature of how the velocity, the distribution, the temperature distribution is seen when film condensation is taking place. Hope you are clear with this analysis. Then here if while the flow is taking place, so we can say it is flowing, it has some mass flow rate, that means that can be laminar or that can be turbulent. So this laminar or turbulent is determined by the Reynolds number, and this Reynolds number, you know, it is rho v d by mu, isn't it? It is rho v d by mu. Then d is the characteristic or hydraulic diameter. Then this hydraulic diameter, if it is a cylindrical kind of thing, it is 4 area by perimeter. If it is a 4 area by perimeter, by substituting the value, we can draw that rho 4 AC rho V by P mu. Then 4 P V delta by mu or 4 m dot by P mu. Okay, so the Reynolds number, it is directly given by 4m by P mu. So what is DH is 4 area by P or 4 delta. So here you simply wrote it as 4 delta. Delta equals to area by P. Then this 4 delta, then rho AB. Rho AB equals to m dot, then P mu, then 4. So this way the Reynolds number is converted to 4m dot by P mu. P is perimeter. If it is a circular, then P will be pi d, then 4m dot by pi d mu. As you will remember while studying, during the convection, I have discussed that Reynolds number is 4m dot by pi d mu, and this is how it has been derived. So rho Vd by mu, d is hydraulic diameter, that is 4 area by perimeter, then rho Av is mass flow rate, 4 into m dot by P mu. So these are the nomenclatures that has been given. If you will see, then for some different bodies, there are some hydraulic diameter given. If it is a flat plate, then the perimeter is equals to, the thickness is delta, the plate, suppose the width is L, then area equals to L delta, and the perimeter is equals to L, then hydraulic diameter is 4A by P, that is equals to 4 delta. So here P equals to weighted perimeter of the condensate M. Then similarly, if it's cylinder diameter D, this is the thickness that is forming across the cylinder, then perimeter P equals to pi D, then area equals to pi D into delta, then 4A by P, that is equals to 4 delta. 4A by P, A is pi D delta by pi D, pi D cancel, that is 4 delta. Similarly here DH is equals to 4A by P, area is L delta, P is L, then 4 delta. Similarly, if the cylinder is kept along horizontal along its length, this will be the film that is forming. Then again the perimeter is equals to 2L, and the area of cross section is equals to 2L delta, then DH equals to 4A by P, that is equals to 4 delta. So here the perimeter, that is the perimeter of the film that is being formed, that is 2 into the length, that is this plus this, 2 into L, and area of the what is AC? AC is the P into delta, that is weighted perimeter into film thickness. So area equals to this side and this side, 2L delta comes over here, that is equals to 4 delta. So it will be 4A by P or 4 delta. If delta is given to you, you take directly delta. If delta is not given to you, you can take it to be 4A by delta. You can calculate the area by the formula 2L delta, or the area that has been given here, and the perimeter equals to L pi D or 12. Here the perimeter and area, if you will see, remember P is the weighted perimeter of the condensate, that is the film, and AC is the weighted perimeter into film thickness of the condensate at the lowest part of the flow, at the lowest part of the flow, lowest part of the flow, lowest part of the flow. So this is how you are going to calculate the perimeter and area during this condensation. Hope you are clear with that. So when the final state of subcooled liquid instead of saturated liquid is formed or obtained, then the latent heat of condensation is given by HFG plus 0.68 CPL Tsat minus Ts, and this is the modified latent heat of vaporization, and this is an empirical correlation that has been obtained by the experiments. So instead of directly using HFG, you can use this formula 0.68 CPL Tsat minus Ts, where Ts is the T surface, CPL is the specific heat of the liquid, and HFG. Supposing if the vapor that enters the condenser is a superheated vapor. Superheated vapor means, if you will see the Ts diagram again, what we see here, this is the dome, constant pressure line, then this is the subcooled, this is the phase change process, and this is the superheated, this is the saturated liquid here, saturated vapor, this is superheated. If this is reducing from the superheated, then here there is a sensible heat loss, then here there is a latent heat loss, then again something that is sensible heat is there. So here there will be normal HFG, then the HFG because of this latent heat, because this sensible heat comes into picture. HFG stands for the latent heat and the sensible heat that is coming. Then again here it will be the sensible part of this superheated to saturated condition. These three things will come into picture. Here this one represent these regimes where the heat is being transferred from the superheated to saturated, and this terminology of HFG determines the condensation from this point to this point. Hope this is clear to you. Then the rate of heat transfer or Q condensation is H AS Tsat minus Ts equals to m dot into HFG star. You got what HFG star is. Then Reynolds number can be the Reynolds number is 4Q condensation by P mu HFG, and by substituting the form you get here, then the T fluid is To estimate the Reynolds number, we need the property mu. This mu and all are calculated by the T fluid, and the T fluid is assumed to be the mean value of the saturation temperature and the surface temperature, and this TF is called as the film temperature. That is the temperature at which properties are determined. So this equation is used to determine Reynolds number when the condensation heat transfer coefficient and rate of heat transfer is known to you. And typically this is a 2 mark of GATE question, that how you can get the Reynolds number by using the condensation rate, that is the rate of heat transfer, and the condensation heat transfer coefficient is known to you. So this is equals to 4AH Tsat minus Ts, AS Tsat minus Ts divided, we know that RE equals to 4 m dot by P mu. Okay, then what does it did here? It did what? It multiplied here into Q condensation, that is the rate of heat transfer during condensation, divided by the HFG star, that is the latent energy that is being applied or being used here, into m dot. This m dot get cancelled, and it is 4 into Q condensate by P mu HFG. So this is how this thing comes into picture. Reynolds number is 4 m dot into Q condensation, that is rate of heat transfer, by P mu into the condensation heat transfer, that is the amount of the latent heat energy that is being transferred during the condensation process. So Q HH delta T equals to m dot HFG, that is rate of heat condensation. That means this HAS Tsat minus T infinity by m dot HFG, if the rate of heat, that means this will equals to this. So it takes the ratio of this divided by this and multiplied it with 4 m dot by P mu, and you get this Reynolds number. And this relation 4 m dot by P mu, that you can use to determine the Reynolds number. Else you can use this correlation. This is an empirical correlation suggested by that is a modified Reynolds number by the usage of the condensation heat transfer coefficient, or the rate of heat transfer is known to you. So we will study the flow regimes. Like the film is forming over the surface, there will be laminar and turbulent regime. So let's see for a condensation of film wise how the flow regimes are there. So initially the flow will begin, the delta will gradually increase, and it will reach a value where it ends, and beyond that the delta doesn't increase, and suppose that is the end point. Then initially the Reynolds number will be 0, and the film that is forming, that will be free of waves, and this is called as the wave free regime. And the Reynolds number here is nearly equals to 30. Then beyond this wave free regime, there is a laminar wavy regime. It is still the Reynolds number equals to 1800, less than 1800. When Reynolds number increase the term 1800, the film condensation over a flat plate becomes turbulent, and this is given over here. You can means like remember those magnitude, like for a flow through cylinder, critical Reynolds number is 2300. For flow over flat plate, then the critical Reynolds number is 5 into 10 to the power minus 7. 5 into 10 to the power 7. Then for flow regime during the condensation heat transfer, the laminar wavy, when it terminates and form the turbulent, the Reynolds number critical is 1800, and that can be estimated by the formula 4 m dot by P mu. Then we will see some of the heat transfer correlations for vertical plate. So we will assume that the vapor and plate are maintained at T surface and T saturation. Here the heat transfer liquid film, as it is a film, we will assume the mode of heat transfer is completely conduction and the velocity of vapor is 0, so that it exerts no drag in the condensate and no viscous force here is there at the liquid vapor interface, and the flow of condensate is laminar, that is the Reynolds number less than 30 degree, and the condensate layer's acceleration is also negligible. Then let us consider an element Vdx. At the surface the velocity is u, so u0 at y equals to 0. Then the surface temperature is Ts, gravity is acting downward at the interface of the liquid and vapor. The T saturation is there, temperature is equal to T saturation. And if we will see the force balance of the element, supposing if this height is dx, this length is delta minus y, then the shear force will be acting in upward direction, and by the Newton's law of viscosity, it is, I will try to hope this is now visible to you. Now this element, this length is delta minus y, this height is dx, then the flow is happening in this direction, so the shear force that is acting across the element will be, as per the Newton's law of viscosity, shear force will be mu du by dy into dA. dA area equals to b into dx. Then weight of the element will be acting downward. What is the weight of the element? That is equals to rho g h. Then this rho g h is the pressure into area, the body force that is acting downwards, rho g delta minus y into dA. So it is basically rho g v. We express the volume as h into area, that is delta minus y into b dx. Then buoyant forces also will be acting in the upward direction, that is rho g delta minus y into b dx. Here, as the film is flowing downward, the density will be of the density of liquid. As the buoyant force of the vapor is acting in the upward direction, the density of the buoyancy force will be rho v. So by balancing this equation, by doing this force balance equation over here, we can estimate the how the force is being acting on the condensation process, and the average heat transfer coefficient for laminar film condensation is given by H vertical through this correlation. Okay, this is an empirical correlation estimated by the experimental observations, and the value of HFG star is this, that is the modified, and if superheated will come, then plus CPV TV minus Tsat terminology will get added to here. Then Reynolds number will become 4g rho L into rho L minus rho V delta square by 3 mu square. So it can be represented in this from the H vertical is near equals to 1.47 KL RE to the power minus 1 by 3 G by V1 square to the power 1 by 3. So this is how the convective heat transfer coefficient for a vertical plate can be given on the basis of the Reynolds number, acceleration due to gravity, kinematic viscosity, and thermal conductivity of the liquid. And all the thermophysical properties of the vapor and the latent vaporizations are estimated corresponding to the saturation temperature. Then we will move on to the Wavy laminar. For the Wavy laminar flow, this is the equation for the convective heat transfer coefficient. In your GATE examination, laminar question may come, but Wavy laminar, it's very difficult to be asked. If it is asked to determine, then all those property will be given to you, but you can remember the formula so that at least you can recognize, okay, what does it symbolizes there. Then we will move on to the turbulent flow on vertical plate, and for turbulent flow, this is the empirical correlation that has been given for the condensation mode. And this equation is just for your knowledge. Question have never been asked till date on this part, but never know. if it can come. Then we will move on to the vapor velocity, on the effect of the vapor velocity on the analysis of this condensation. So we have assumed while determining this force balance and all, the vapor velocity is so small that it is neglected. Why? So that the drag that is exerted on the liquid film will become negligible. However, the vapor velocity is high, the vapor will pull the liquid at the interface along, since the vapor velocity at the interface must drop to the value of the liquid velocity. Your vapor velocity is there, then at the liquid vapor interface the vapor will try to pull the liquid, isn't it? So if the vapor flows in the downward direction that is same in the direction of the fluid, then it will increase the average velocity of the liquid, so the delta will reduce. See how? Suppose this is a plate and this is the film that is forming. Suppose the air is also flowing in this direction, the vapor is flowing in this direction, then it will make the film to fall at a faster rate, so it will not give enough time to grow to a longer time, so the delta will be smaller. But if the velocity is reduced as compared to this, then it will give some longer time for this film to formation and the delta will increase. So if the flow velocity is in the vapor is higher and the vapor flows in the same direction as per the film, then with increase in the vapor velocity, the thickness reduces. And if the thickness is reduced, the thermal resistance of the liquid film will also reduce. Supposing if the film is forming in the downward direction but the vapor is going up, then what will happen? The vapor will exert a force on the liquid in the opposite direction. When the force is exerted, the film thickness will increase. This will decrease the heat transfer. That means if this is the thing and plate and vapor is flowing in this direction and film is forming here, this will push the layer and it will try to widen it up. More it will widen, more the heat transfer drop or the decrease in the heat transfer will take place. That means if the flow of vapor is parallel to the direction to the flow of the fluid, the thickness of the film reduces, increasing the heat transfer. If the flow of vapor is in opposite to the flow of film, then the thickness widens up and it causes reduction in the heat transfer. Now we will again analyze another effect, that is the presence of non-condensable gases in the condensers. In the condenser, supposing if in the room we have air have in different gases, one of that is water vapor. Supposing if there is some gas which is non-condensable at the temperature in which the water vapor is getting condensed, then what will happen? These non-condensable gases, what does they do? That the presence of non-condensable gases affects the condensation heat transfer. How? Now this drops the convective heat transfer coefficient. This non-condensable water vapor, it has its own thermal conductivity. When non-condensable gas acts to that, the equivalent thermal conductivity will get reduced. If the equivalent thermal conductivity reduces, then the overall heat transfer from the surface to the from the surface to the air or the condensate that is forming, that will reduce. So the heat transfer, the addition of the non-condensable gases causes significant drop in the heat transfer coefficient. So the heat transfer in the presence of the non-condensable gas strongly depends on the nature of the vapor flow and the flow velocity. For high flow, the velocity, it's remove the stagnant non-condensable gases from the vicinity of the surface and improve the heat transfer. So the here you come to know how these non-condensable gases are affecting this heat transfer coefficient. Now we will move on to drop-wise condensation. As you can see a picture, it is a copper surface in which liquid drops are formed. So in the dropwise condensation, it is seen that the countless droplets of varying diameter are formed on the condensate surface instead of liquid film. One of these droplets formed on the same nucleation, the vapor bubbles are forming in the nucleation sites, the droplet will form if the roughness is not there, drop-wise condensation won't happen. So as the drop-wise condensation is taking place here, it has some of the area remaining between the droplets that can make the heat transfer to occur, and this area will enhance the heat transfer. So the convective heat transfer coefficient of this drop-wise condensation is higher as compared to the film condensation. And here one more thing is that the difficult part is not to generate the droplet. The difficult part is to sustain the droplet for a longer period of time. Because if you will see, this is the surface, droplets are forming. Once it reaches a particular size, it will fall down because of its own weight and because of the gravity. So to hold a droplet for a longer period of time in order to have a greater heat transfer, it is quite difficult. So with this, we are done with our phase change process heat transfer. And if you want to see, this is the value of the dropwise convective heat transfer coefficient in the dropwise dropwise condensation process, and for the film wise we have discussed. So with this we concluded with our phase change processes, that is with the boiling, evaporation and condensation. So now we will be solving some of the GATE problems here related to this phase change process heat transfer. So let's move on to our first question, that is related that is asked in GATE examination of 2019. Okay, that pool boiling, the question is pool boiling equipment operating above ambient temperature is usually designed to operate. Pool boiling equipment designed to operate above ambient temperature is usually designed to operate, option A, above critical heat flux, B, near leaden frost point, C, above leaden frost point, D, near critical heat flux point. So the pool boiling equipment designed to operate above ambient temperature is usually designed to operate at which condition? We know, as if you will remember the pool boiling curve, the point of CHF or critical heat flux, it is the point at which the system fails, or heat transfer doesn't happen, and after reaching that magnitude the system fails. That's why that temperature is, that point is called as the critical heat flux temperature. We have discussed it. So all the equipments are designed to operate below the CHF so that it won't rupture or fail while operating. So for a pool boiling equipment designed to operate above ambient temperature is usually designed to operate near CHF, because any system cannot work beyond CHF, and leaden frost point is the lowest point, having the lowest heat flux magnitude. So nothing will be operating near the leaden frost point. So it will be operating near the critical heat flux point, near the CHF point. Fine. So now let's move on to another question. Okay. So the second question that has been asked in GATE 2018. Okay, so you can hear the question. Vapor bubbles are formed in the nucleate boiling regime at a frequency of 10 bubbles per second per nucleating site. So bubble is forming at 10 bubbles per second per unit square of the nucleating site, and there are total 100 nucleating sites per unit area. So total bubbles are 10 bubbles per second per nucleation site, and one nucleation site there are 100 nucleation sites per unit area of heating surface. The latent heat of vaporization and density of vapor under the operating condition are 1000 and 1 kg per meter cube. So density is equals to 1 kg per meter cube, and latent heat of vaporization is equals to 1000 kilojoule per kg. Then it is given the diameter of the bubble is equals to 10 to the power minus 3 meter. Assume the entire heat supplied is used for vapor generation. The entire heat that is supplied is used for vapor generation. That means no heat loss is there. The heat flux in watt per meter square of heating area is how much? So the heat flux is equals to how much watt per meter square. So here total there are 100 nucleation sites per meter square, and from one nucleation sites 10 bubbles are departed in unit time. So total per unit area in a given second, total number of bubbles that are departing is total number of bubbles departing per unit second from the unit area is equals to 10 into 100, that is equals to 1000. We know the diameter of one bubble is this. So the total bubble, the heat flux, the bubble A, then we have to find out that what is the heat that is being, then that this is normally equals to m dot into HFG. M dot is equals to what it will be? Rho into HFG. So that is 1 into if we will be going towards the volume of this droplet, that will be 4 by 3 pi RQ into the total number of bubbles nucleating per meter square of area into HFG, that is equals to 1000 into 10 to the power 3. So this will give you the answer, isn't it? So this is how it is going to work it out for here. Try to solve it and the answer will be 0.523 watt per meter square. Now another question, let's move on. It has been asked in GATE 2017. Then here it is said that a steam is at 100 degree Celsius. Then it is condensing on a vertical plate. Okay, then the condensate flow is laminar. That means RE is equals to 30. Okay, the average Nusselt number N1, NU1 and NU2 when the plate temperatures are 10 degree and 55 degree Celsius respectively. So the temperature 1 is equals to 10 degree Celsius, temperature 2 is equals to 55 degree Celsius, that is temperature of the plate. Then assume the physical property of the fluid and the steel remain to be constant with the temperature of interest. That means the thermophysical properties are constant, no variation in the temperature. For a film time condensation, what is the ratio of NU2 and NU1? Remember, if you will remember the equation we have studied, Nu is proportional to delta T to the power minus 1 by 4, isn't it? Then delta T1 is equals to 100 minus 10, that is equals to 90. Delta T2 is equals to 100 minus 55, that is equals to 45. Then Nu2 by Nu1 is equals to delta T2 to the power minus 1 by 4 by delta T1 to the power minus 1 by 4. Put the value and you will find it. It will be something 1.189. That will be equals to some the value will be 1.189, and as per the given solution it will be nearly equals to 1.9. So with this we have tried to solve some of the GATE previous year question. Hope we are clear with how the theory means, like it is application of the primary theory that we have discussed, and everything is there in the class that we have all studied here. So in this manner we have completed with this phase change processes. So now I will give you a brief introduction about what we will be studying in our upcoming classes. Is that we studied about evaporation, we studied about condensation, we studied about boiling, then we have studied about conduction, convection and radiation. So with agglomerating these two terminologies, all those fundamental concepts, we will be applying it to a very much application process, that is the heat exchangers. So here we are going to study about the heat exchangers. The heat exchangers are the devices that will incorporate the conduction convection mode of heat transfer if the energy is very high, that can incorporate the radiation mode of heat transfer also, and in the heat exchanger sometimes phase change also takes place, that is maybe condensation, maybe evaporation, or maybe boiling can takes place through that. So now we will be coming towards the application part of this overall heat transfer that we have studied till now, and that are the heat exchangers. So these heat exchangers we will study the types, the categories, how the heat transfer is taking place, the energy balance equation, and in the convection we have studied the LMTD. That's application we are going to study over here, that why we have studied how that LMTD is being applied towards the analysis of heat exchanger. So in the next class we will be discussing about what heat exchanger is. Till then, have a go through to this phase change processes, and if you feel any kind of doubt or confusion, feel free to ask me. Thank you and have a good day.